Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at the algebra of Riemann integrability, meaning suppose we are given two Riemann integrable functions. What can we say about the Riemann integrability of their sum and their product? So let us recall some notations. We have a bounded function, and suppose sigma is a subdivision of the domain of the function. Then we define the upper sum corresponding to that subdivision, upper sum of f corresponding to that subdivision. Today the subscripts will matter, so I'm putting the subscripts. So that is defined as this summation, where the first guy, again there's a superscript and a subscript, is the supremum of the function over the ith part of the subdivision, and this is the length of the ith part. Similarly, the lower sum of f corresponding to sigma is this summation, where the first thing is the infimum of f over the ith part as written here, and this is again the length of the interval, the length of the ith part of the subdivision. We define the oscillation of f corresponding to sigma as the difference of the two things, the upper sum and the lower sum, which one can expand out as that, where this term we write as omega I f sigma. So this is a notation that we'll use. It will be very convenient. And last time what we saw is that f is Riemann integrable if and only if this happens, which means what? Which means that for all epsilon greater than 0, there is delta greater than 0, such that whenever norm of a subdivision is less than delta, we have the oscillation corresponding to that subdivision is less than epsilon. So f is Riemann integrable if and only if this verbose thing happens, which we abbreviate by writing that. Alright, so these are the two problems for today, and we'll be using both of them. These are very simple problems we'll be using in today's material. Okay, so the first proposition is, suppose we have two Riemann integrable functions, then we want to show that their sum is also Riemann integrable. Okay, so here is the thing. So first we have, and there is no need to write first, we have, so let sigma be a subdivision. Then this is at most that. This is one of the problems above, the first one, or no, rather the second one, this thing, and we will also use that. So we also have the other direction. Right. Therefore, if we take the difference, we see it is less than just playing some basic algebra. Which is same as writing this. And therefore, since this is always non-negative, the oscillation is always non-negative, therefore limit n sigma going to 0, wf plus g, sigma is 0. Because these two individually get killed, and this sandwich now tells us that this will also go to 0. So very simple. Okay. A little bit more involved will be this one. So okay, let's prove this. what we are saying is, suppose we have a Riemann integrable function, then its absolute value function is also Riemann integrable. So first note that something very general is that recall that alpha minus mod beta is less than equal to the difference. This is for all real numbers, alpha and beta. This is one way to state the triangle inequality. In fact, I can also put an absolute value here, but I don't think I need it. So we have that true for all real numbers. Therefore, in particular, we'll have this is for all x and y in the domain. Okay, so we have this some general thing. So now let sigma be a subdivision. And say sigma is, just for concreteness, let us say it is equal to that. All right. So then we have this for all x, y in the ith part of the subdivision. So of course we have this. And now what I'm going to say is that this is at most this minus that. So this is the supremum of the function over the ith part. This is the infimum of the function over the ith part. And we claim that that is less than equal to that. And this is again very easy. So let me just argue, not very formally. The thing is, suppose fx is at least fy, so you can remove the absolute values basically. Then this guy is dominated by that, and this guy dominates that. But since we have a minus sign, we would have this guy is dominated by that guy. So therefore we have that. And if if fx were less than fy, then do the same argument for fy minus fx, because when you take away the absolute values, it will become fy minus fx, and we have this. So this is a very simple inequality. So this also holds for each x and y in the ith part. So we have that, and therefore this implies supremum. I'll just take the supremum over x over the ith part. Maybe I should write it in this fashion, it looks neater. Minus fy. This is, as I introduced this notation, instead of writing that, I will write this. This is for all y in the ith part. I've already taken the supremum over x, and this implies, well, the supremum is mi mod f of sigma. And now I can take infimum over y. Okay, let me write it that way. Yeah, so there is no for already taken infimum, so we have this, which is same as saying this, which is same as saying that. And therefore this summation also gives the same inequality. Which the left side is nothing but the oscillation of mod f over sigma, and the right side is the oscillation of f over sigma. So basically this was the point. I mean, you could have, if I had just given this as an exercise, everybody would have solved it. But anyway, I decided to give the full details. So we have that, and therefore since f is Riemann integrable, the limit of that guy goes to 0 as the norm of sigma goes to 0. So because of this sandwich, the limit of mod f also goes to 0 as the norm of sigma goes to 0. Which implies Riemann integrability of mod f, and we are done. So very nice proof. Very simple estimates, but nice. And this one is also very interesting. So this time we want to show that if f is Riemann integrable, then f square is Riemann integrable. Okay, so fine. So let sigma be a subdivision. Then, well, this is a very basic. Let me write it this way. This is fx square minus fy square, or maybe that was better. It's the same thing, but just notation is a bit different. So this is equal to, by high school algebra, okay, so before I write this is true of course, but before I write this, let me say that let k equals supremum of mod fx over its entire domain. So it's a number because f is a bounded function, so it is some number. And now we do this business. So this is true. Well, this is true for all x, y in the domain, but let me just say this is, I will use this only for all x, y in the ith part. So we have that, but this implies f square x minus f square y is less than equal to fx minus fy times 2k, because that is less than equal to k and that is less than equal to k, so this is at most 2k, which implies, yeah, so this is, I'm using this for all x, y in the ith part. Which is less than equal to m fi sigma minus m fi sigma. times 2k. So because this is at most that, this is all that I'm using. So again, this is true for all x, y in the ith part. So the rest of the proof is just like the previous one. So I can take this supremum. I'll skip one step and take the supremum and infimum both at the same time. And this is of course mi f square sigma minus little mi f square sigma, which which I will write as omega if sigma 2k, which gives us omega I f square sigma 2k omega I f sigma, which implies I can do this with the summation. Let me take the 2k out. I'm sure you see where this is going, but just to have a clear conscience, I'm writing the full details. Which is the oscillation of f square or sigma is less than equal to 2k oscillation of f over sigma, and therefore again it's just like in the previous proofs, this thing is equal to 0 because f is assumed to be Riemann integrable. So this limit goes to 0, and now this sandwich tells us that that limit goes to 0, and we are done. Okay, great. And now let us show that if we have two Riemann integrable functions, then their product is also Riemann integrable. So this will be a one-liner. So note that. The product is 1/4 of f plus g whole square minus f minus g whole square. Okay, this is again basic algebra, and we have already seen that if f and g are Riemann integrable, then this is Riemann integrable, and since this is Riemann integrable, its square is also Riemann integrable. So this guy is Riemann integrable. Similarly, since f and g are Riemann integrable, their difference is also Riemann integrable. We did not state it, but since g is Riemann integrable, its negative is also Riemann integrable. That's a simple thing. So therefore this difference is Riemann integrable, and hence this square is also Riemann integrable by the previous lemma. So this whole thing is Riemann integrable. But if you scale a function by scale a Riemann integrable function by any real number, then again you get a Riemann integrable function. This is the first problem. This thing. So therefore fg is Riemann integrable, and we are done. Okay, and let me do one more. So let f and g be Riemann integrable. Then so are the max and the min functions. So what do I mean by this notation? This is a function max f comma g is a function from the common domain which takes x to max of the two values that we obtain Similarly, you can define min. So I'll prove that this is Riemann integrable. This will have a very similar proof. So here is the proof. So max of any two real numbers is half of mod of a plus b plus mod of a minus b. So that's just a very simple identity, because if suppose a were greater than or equal to b, then this side becomes a and this side also becomes a, because this absolute value goes away, and yeah, what am I saying? So if a is greater than or equal to b, then this becomes a minus b. And does that become a plus b? What is wrong with me? Minus 2 and minus 3. So that's 5 plus. Okay, so this is all that I wanted to say today. As usual, like, comment, share, subscribe. So this is all that I wanted to say today. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the. See you next time.